Welcome everyone to our lecture, engineering lecture series. And this particular lecture is very important because it's prepared for sophomore, uh, like students who are entering from high school to the university engineering programs, engineering technology programs, or different type of programs, and they're at a point of making a career choice, a decision to their career. So, very important lecture, and the entire purpose of this lecture is primarily uh, to try to passionate the students on the importance of electrical engineering, electrical electronic engineering, computer engineering, and related courses which is offered by different faculties around the world and in different departments. So that is kind of a brief overview of how this lecture is prepared. So it's not focusing only one particular course. It's basically focusing the program, the outline offered by the department relating to, again, electrical, electronic, computer engineering, and technology related courses. And that's why this slide is showing you that it's going to talk about embedded systems, digital analog, electronics. When we talk about digital or analog electronics, we are talking the fundamental seed of those is basically transistors onwards to op amps, this and that. Then we are going to talk about microcontrollers, FPGAs, PLCs, stands for programmable logic controllers. FPGAs stands for floating point gate arrays, and robotics. Okay, so one of the most important aspect of whenever you're reading, listening, uh, anything is to understand the meaning of the words. So that is what right at the bottom it says that anyone interested in understanding the meaning of a word, you go to kind of Oxford Dictionary, go Wikipedia, or simple Google search for the word like microelectronics, what is embedded means, what means by digital, what means by analog, or what means by electronics. From there, from where those words originated, will tell you a lot about the meaning, not only the meaning, but how and why those words are used in the offered courses. So again, very humbly request all the listeners to try to understand the origin of the word, which gives you in a very short time a lot of information. Okay, so let's carry on with the next slide. So we are still here. So uh, why I have this word data on this particular slide? Because whatever we are talking, whatever we are learning, whatever we are doing, you will find that data we are doing we're doing it under the word of data, and I will soon in the next slide I will talk about that. So data is a very important word. Whatever you're learning, whatever you're reading, whatever you're trying to do, data is a is a seed of all those things. So that's why we are also going to, whatever I'm presenting, data is central to that. And that's when we talk about data, then we talk about the science, analytics, analysis, or engineering related to that. So that is the reason all these kind of words are put in there. So it's basically kind of a package in a very short time to try to passionate you, motivate you in your decision making process or in your selection process, that what you want to do in your career or with your life. Okay, so let's carry on. So, so when we talk about these words, as I said, data science, analysis, engineering, so basically, primarily, they're all connected with, which is nowadays very kind of popular, words, which is AI for artificial intelligence, ML for machine learning, and DL for deep learning. So kind of a very important keywords to understand in anything what you are doing with a course, with a career, with the work you are doing. Okay, so let's move on. So we deliver such knowledge and courses under the umbrella of Contact Field Institute, and what we believe in, that there is no shortcut to glory, and that's what this word is. So you have to work hard, you have to understand what you're doing, and it takes time in achieving desired objectives. So there is no shortcut, so make sure that whatever you learn, whatever you do, you try to do the best you can, okay, and try to learn. This is our LinkedIn page. Soft Galaxy Technologies in Canada is Contact Field Institute is basically under the umbrella of Soft Galaxy Technologies Inc. These are the emails: info@hsclouds.org. HS stands for Humanity Serving Clouds, or softgalaxy.hsclouds@gmail.com. Let's carry on. So let me pause it. So let's start the slideshow again. So this slide is regarding the career objectives. So so what is it's showing you that the courses and career objectives relating to getting comfortable with electrical, electronics, computer, automation, engineering, technology knowledge for any kind of client's projects and program needs. So whenever we talk about clients' projects or programs, the needs of the clients are going to be either industrial or consumer applications. So basically, with this kind of program, electrical engineering, electrical electronic engineering, electrical electronic computer engineering, or technology related program you will take, it will basically give you a self-reliant and confident start in a professional journey. And the best way to, in my opinion, to get you motivated is to show you what those programs can do. So let's talk about that. So here are some demo videos I'm going to show you there. So this is an Amazon kind of a fully autonomous warehouse which is operated by robots. So it's going to take you few minutes, but those are very important minutes for individuals to concentrate on. So let's look into this video. So as you can see here, these are all the robots operating. So that's what kind of a robotics knowledge can give you. Okay? So what you see there, the robots are operating, but one of the key elements of the robot are the motors, the switching, okay, the PLCs. And that's what basically pertains or relates to electrical, electronic, computing technology, or engineering. So how to prepare such robots for the automation task, how to repair it, are the fundamental aspects of to get a job related to that. So this video showed you kind of what you can get as a skill relating to the selected program. Okay, so let's talk about this. This is a grocery store in UK, very popular, famous. What these robots are doing. So let's listen to that.
What you're looking at behind me is the hive. We've got the grid, which is the metal structure. It's filled with product. So that product is housed within what we call totes, or these open boxes that you can see at the top of the grid. We have around 2,300 bots and they move the stock around the warehouse so that we can pair it up with customer orders to be delivered. The bots will move in the X and Y direction. They can also move in the Z direction. So we have a cable hoist system that means that they can lower down a gripper assembly and grab onto the stock that we have in the grid. In some areas we have as deep as 21 totes all in a line. We have sensors underneath the bot that mean that every time it passes over one of the squares on the grid, it has a laser underneath it that can tell when it moves over that cell. So it will say, I've passed a cell, I've passed a cell, I've passed a cell. We have around 58,000 different types of individual products within the grid. We'll use the huge amounts of data that we gather to understand what customers are most likely to order and place them in the easiest to reach locations for bots. All of that combined means that we can have stock into the warehouse and out again from our suppliers into a delivery van in just 5 hours.
The robots deliver their crates over to the packing area. Some of that packing is done by humans, but there are mechanical arms as well. One of the big problems they've got to solve is that grocery packaging.
So I think that's enough for the demo on this side. So what do you see here again? Kind of a robotics working to pick customer's order and deliver it to the shipping guys so that they can ship it to the respective destination. Again, relating to the program, we are talking electrical, electronic, computer engineering, and technology, and that involves all the keywords what I have mentioned right in the beginning of the slide. It talks. That thing what you have seen in itself is an embedded system. It has many embedded systems. You can see we can talk about. It has digital analog electronics. It is using microcontrollers, FPGAs, data-driven AI, ML, and DL, potentially DL as well. Okay, so let's talk about the driverless autonomous taxi in Los Angeles. So let's look into that demo.
There is no more wait list. There were 300,000 Angelenos on it at one point, but now anyone can get a robo-taxi in this 80 square mile zone that essentially stretches from Santa Monica to downtown LA. And I have to admit, I've been on the fence about getting in one of these things. I've seen them everywhere, but tonight I finally had to try it.
It is the most advanced, fully autonomous driving technology in the world today.
And now it's available to everyone in LA.
It's designed to be really easy to use. All you have to do is download the app, put in your information, and then request a ride. Now, I've done this several times, and it keeps saying that there's server errors, but now it says I have a ride coming in 2 minutes. And there it is. I almost want to wave to it, but obviously there's nobody inside. But I know that this one is mine because it has my initials right there, CE at the top. So I should just be able to unlock it on the app. Pretty cool. Let's check it out. All right, so inside we've got nice music playing, obviously no driver, and I've got the prompts here on the screen, so let's start ride.
Hello from Waymo. As we get going, just give us 1 minute to cover a few riding tips.
After some safety reminders, we were off through the Fairfax district, navigating through hundreds of cars and pedestrians. Our car did have to honk a couple times.
It's honking at that car. Oh man, look at that. Oh my gosh. Oh my god.
But all in all, it was a smooth trip.
Got temperature control. Not gonna touch any of those, obviously. Ooh, making it nice and warm. I'll hold it.
Angelenos seem mixed about whether they're ready to try it.
It just doesn't feel right. It feels like no one's in control.
I trust it enough.
Oh, because I would be too scared to get into a car with nobody driving it.
Would you get in one of these driverless cars?
I would. Yeah, I actually do sometimes. It's pretty fun, and my mind was blown the first time.
His mind was blown. I have to say, ours kind of were too. It was a pretty incredible experience. Now, again, this is only available in 80 square miles of LA County right now. It doesn't go to the Valley, for instance, or South LA. It also does not do drop-offs or pickups at LAX, and it doesn't go on freeways. But, of course, the company says this is only the beginning. Reporting live from the Fairfax district, I'm Chelsea Edwards. Send it back to you in the studio.
So would you ride it again? And how do you compare it to like an Uber?
I have to say, the great thing is, Alex, you don't have to talk to anyone when you're inside. You change all the settings yourself, and it's just quiet. It's just a very peaceful ride. So I could definitely see myself using it again. Yeah.
So again, what you're seeing here is primarily it's something new. People are not used to it, so that's why people's concern whether they're going to use it or not. But overall, once the confidence level reaches beyond the threshold, the concerns of the public, it's going to be pretty normal. But again, this is the kind of a technology. This is the kind of industry which is basically heavily dependent on the programs like electrical, electronic, computer engineering technology, driven primarily by data-driven words like data science, analysis, engineering, AI, ML, and DL. So let's look into this one last demo video. Again, this robotics, I'm a big the kind of work they've done, amazing. Boston Dynamics. So let's see what this robot is doing. Let me maximize it. And so this gentleman is
forgot my tools again.
In a warehouse. He forgot something, and he needs someone to help him out. So here you go. The robot is going to help him. So he sent a command to the robot. Given him the toolbox he's looking for, come down. That's amazing. So
Such a show off.
That's amazing. That's the kind of the knowledge you will acquire when you will join a program like electrical, electronics, computer engineering, or technology a program. Okay, it has, as I said, it has a lot to do with the keywords which I have mentioned right at the beginning. Okay, so with this demo, so let's move on. There are other demos as well, but I think we are short of time, so let's keep on going to the next slide. Here you go. So let's talk about some of the very fundamental knowledge which is very important to be clear on. And so the most important question is, I want listeners to understand that what is analog. So understanding this will really help you understand some of the other keywords we are going to discuss. Okay. So what is analog? So analog is something which is continuous. There are no breaks in it. So one of the example is time. So time is continuous. There is no breaks in it. So whenever we tell time that whenever we ask or tell a time, that's not analog, and I'll tell you why. Okay. So here's what it is. Okay, so we know that as scientifically, that it's the Big Bang which started, let's say, time and all the way in different phases, all the way to the planet where we live in. Okay, so what is Big Bang? Big Bang is basically the birth of data. That's exactly what it is. So, so it means whenever we talk about any field whatever we learn, data is basically integrated seamlessly in those subjects. So that is the importance of data. So the universe is primarily, so what you see that this picture is basically the picture of the kind of an overview picture of the universe, giving you an overview that it started with the Big Bang and going you in one direction, different phases. This is all talking about different phases, and we are not going to go into the details, and eventually coming into the planet Earth where we live in. Okay, so our universe is basically analog, and that's exactly what it's showing. And this universe is governed by the beauty of math and physics. And what I believe in this is that math is the language of the universe. Okay, physics extract the knowledge hidden, and math is the language we use to describe that knowledge and to understand that knowledge and to convey that knowledge to the coming generations. Okay, so that's what analog means. So when I was saying that time is analog, and whenever we tell someone or listen to someone telling time that okay, it's 3:15, 4:15 p.m., a.m., whatever, so we are right there, we are discretizing the time, because we are not telling that okay, we are only telling it's at that many hours, that many minutes, and that many seconds. But beyond seconds, we have the time is continuous. We can, if you want, we can keep on telling, okay, there's so many milliseconds, picoseconds, femtoseconds, blah blah blah. So it will be a time which is basically, we can keep on telling. It doesn't have a discrete, but we make it discrete. Why we make it discrete? Because it's easy to convey the information, and it's easy to understand. So what is the key point? That we discretize information for our comfort and ease. So that is the most important thing to understand. Universe is analog. We work in the digital domain, discrete domain, to make things easy for us, comfortable enough that that's adequate information to use for further doing our work or enhancing our knowledge. Okay, let's carry on. So what is an analog signal? So what you see here is basically an analog signal. It has voltage on the y-axis, time on the x-axis. So it's going. We are going to learn that how we are going to make an analog signal discrete. For that, we use a device what we call it as analog to digital converter. So the only thing that it does, it takes an analog signal and gives an out. In this case, it's a 3-bit analog to digital converter. So it's going to give 3 bits word as a digital word at the output. So what this means, that this ADC is going to convert this signal, what you see here, this signal, into 3 bits. And as you can see here, in binary, this is 0, 1, 2, 3, 4, 5, 6, 7. So it means this is a value roughly 6, but just below 6. And this is a value of 1, and this signal level is at value 2. So that's how we bring our analog information using different sensors, different techniques, from analog world to the digital world. And that's we do it analog to digital by using an ADC called analog to digital converter. And to go back from the digital domain back to the analog, there is a device what we call it as digital to analog converter. So that's how simple it is to bring the analog information into the digital domain. So why digital? And as I just mentioned, when someone asks you what is the time now, the time information you give is digital or analog, and why we make it digital, because of the size and power. Okay, the power used by the computing power, we use electricity. That's what we mean. So when we talk analog computers, so these are the analog computers. As you can see, they were gigantic, less computing power, very bulky, and the reason behind that was, in the beginning we were using vacuum tubes to build such analog computers. But with the digitization, and now the type of computers we use is basically, as you can see here, they can easily fit in our in our pockets, or laptops, mobile phones, and this is all that all ease is because of our use of transistors, and or the invention of the transistors, and those transistors we use to build ICs. One of the ICs called CPUs, FPGAs, also ICs, microcontrollers, microprocessors. They are all ICs, integrated circuits. We are going to talk very briefly about that as well. So again, why we came from analog computers to digital is because ease, comfort in the size and the power consumption, and removing the bulkiness. As you can see, these cables, these huge panels, as you can see here, the racks. So now, when we talk about digital world, so let's understand what this digital world comprises of, or digital electronics. This slide is showing you the basic logic gates we use to build digital circuits. Okay, the digital circuit means building digital systems like laptops, mobile phone, so on and so forth. So understanding these basic seeds, which we call it as logic gates, to build those circuits, we need to understand that. So again, what you see here, we have an AND gate. So this is just a symbol. Historically been, engineers decided to give this shape the name AND, this shape or symbol the name OR, NOR, NOT, NAND, and exclusive OR. Okay, so these are the basic logic gates we use in building digital circuits. One of the most fundamental one is basically this is a buffer. So what it does? This particular symbol, it has an input A. It doesn't change input. It's just we use it to drive current. Okay, so one of the reason of using the buffer is basically isolation, driving the current. Several reasons, but what it does, whatever is at the input, the digital level, that digital level can be 0 or 1. It's not going to change the digital level. So when we are going to talk about digital level, so it means 0 means 0 volts, potentially most of the time, but it can be negative volts as well. And 1 means, let's say, 3.3 volts, 5 volts, or it can be less than 3.3 volts. So whenever we are talking 0 or 1s, we are talking about digital levels. Okay, so whatever is the voltage level at the input, you're going to get the same voltage level at the output. So means if you get 0 volts, 0. If we have 3.3 volts, 3.3 volts, and 3.3 in this case means 1. So 0 to 0, 1 to 1. The other basic gate is the inverter. So it's basically is going to invert whatever is at the input. If the input is 1, the output will be 0. If the input is 0, the output will be 1. That's exactly the table shows. And these tables, we call it as truth tables. Okay, as you can see here, the word truth table. So any digital I/O relationship we show it using these, what we call it as truth tables. Again, input 0, output 1, input 1, output 0, the behavior of an inverter. Let's go to the next slide and just discuss one more very important gate, but we call it as the NAND gate. And this NAND gate is, why we are discussing it, I'm going to tell you very briefly very soon. So again, it has 2 inputs, but there can be multiple inputs, but in this case we are just showing 2 inputs and 1 output. And this is the equation, the digital equation of a NAND gate. If there is no bar, it's A and B. So this will be a AND gate, but with a bar it will become, a bar shows the inversion, the NOT operation. With a bar it becomes a NAND gate. And that's a truth table. And as you can see here, the output is always 1, with an exception that whenever the both inputs are 1. So whenever both inputs are 1, the output is 0. Very easy to remember this. Okay, so the truth table of the NAND gate is very simple. Whenever both inputs are 1, the output is 0. Other way, it's all 1, as you can see here. So why we're discussing NAND gates? Because we can use this gate to build any other gate, like a NOT, AND, OR, NOR, exclusive OR. So that is the reason of just discussing this NAND gate. So what information you're getting, this NAND gate is the gate which we can use to build any other logic gate. So that is the importance, very important information knowledge relating to NAND gate. Okay, so let's carry on. Now we have the clarity on the words, that what is analog, what do we mean by digital, and what are some of the basic gates we use to build digital circuits. If any questions, please raise your hand, else we just keep on moving. So let's talk about what is a microcontroller. Its microcontroller is simply an IC. IC stands for integrated circuit, and a circuit is primarily comprises of as you can see here, circuit means that it performs a function, right? So this is a low pass filter, but we represent this circuit as that it's doing a function C1, because this is a circuit C1 and it's performing the function of a low pass filter. This is a high pass filter, again a function. It's a circuit 2 performing a function. We write it as FC2, and so on and so forth. This is a inverting amplifier taught heavily in engineering, computer electronic engineering courses, and let's call this as that this is a circuit performing a function Cn. Okay, so when we integrate all these together, all circuits combined in a small package, we call it as an IC. We can write it as in the integral form, or we can write it as a summation form. Either way, we are basically just combining all these circuits in one IC package. We call it as integrated circuit, and that's how the ICs look like. Okay, as you can see, they are tiny, very tiny. This on your fingertip. Okay, tiny packages, and all these packages, comprise of we build it. When we talk about digital ICs, we are using the basic gates, but there are ICs which we call it as mixed signal ICs, which have also analog components as well. So that's what the meaning of integrated circuit. And so what is a microcontroller? So we just learned about the package, what goes inside the package. A microcontroller is a mix, can be a mixed signal IC, because it can have an EDC, it can have amplification as well. So it can have smaller analog section along with the digital side, but most of the other microcontrollers commonly used for digital applications have only a digital side. Okay, so let's maybe move on. Again, just talking about different packages, comes in different forms and sizes. These are through-hole ICs, SMD ICs, so on and so forth. Again, just showing different packages relating to ICs. And let's talk about the smallest microcontroller IC. So once I prepared a slide, one of the presentation slide, that was one of the smallest microcontroller comparing with the other microcontroller ICs I found. Then in one of the other presentation, again, it's basically just zoom in version to this IC. Then for this presentation, what I found is this recently in March 2025 from Texas Instrument. This is the smallest microcontroller IC, as you can see here. Okay, how small it is? It's 1.38 square millimeter, and it's a 32-bit ARM Cortex M0 chips. Amazing. So So that's a very powerful IC, very powerful IC. Okay, so that's just to show you the packages are the smallest microcontrollers available out there. And why they're getting smaller and smaller is because of what we know as Moore's law, and it was proposed in 70s that the number of transistors which can squeeze into an IC package will basically double. And this law, the Moore's law, is double every year. So this law still holds, as you can see here. And by 2030, I don't know what will happen, but as of these times, the law is holding pretty decently good because of the improvements in how the transistor is manufactured on an IC package. Okay. So let's go to the next slide. Okay, so just just to show that we basically initially we have vacuum tubes, and then from vacuum tubes this is the invention of the transistor, and that basically the brought us to having ICs, transistors going inside the packages, and we have ICs, and these are the different form of transistors which we use. And this is the Ryzen AMD Ryzen microprocessor. It goes inside your computers, motherboards, and this is the Intel i9. May not be the latest, maybe they have some other latest, but anyhow, just to show you, it's basically start using vacuum tubes, analog computers, invention of the transistors, making it small in size and power efficient devices, but very powerful devices in computing power, what we use nowadays. So here you go. Now this is now with these packages overview, kind of a brief history from where we started and where we are now, like vacuum tubes to now using transistors. So this is a basic block diagram of a microcontroller, and what you see here in a microcontroller, we have a microprocessor and ROM, RAM, and I/O kind of circuits. That's what primarily are the basic building blocks of a microcontroller. And this is the main brain of the microprocessor. Is basically the brain of any IC. In microcontroller, it has a microprocessor. But the important thing to understand this microprocessor can only understand a fixed amount of instructions, what we call it as mnemonics, okay? Not unlimited. So this pin is most likely most of the time is the power, to provide the power. This pin is mostly for the ground, and this is the input pin, the output pin. But one pin, depending on the programming, you can make it as an I/O pin as well. Okay, and what microprocessor does, it basically follows this cycle. It basically fetches an instruction from the ROM or RAM. It fetches it, it decodes it. Decodes means understand what it needs to done and then execute it. And this basically is the cycle what happens. And these are some of the examples of the kind of keywords what a microprocessor can understand. These are the keywords relating to data transfer, arithmetic, logic, Boolean, and branching operations. So again, a microprocessor can only understand limited amount of instructions, and that's what we call it as mnemonics. This is just an example of programming a microcontroller. It's a Hello World application, and we are just it's using an Arduino. So that's what it you set up your Arduino for the serial baud rate 9600, and you print a Hello World, and with a delay, and it's a loop. It's an infinite loop, and it's going to just print Hello World again and again with a delay of 1000 milliseconds, means 1 second. So again, this your program writing will go into a compiler or interpreter, It will convert into a machine language. We will put it in RAM, ROM, or flash or SD card, and then the microcontroller, microprocessor, CPU will execute it, and that's what you see on the computer screen as hello world. Okay. So this is an example of a blinking LED application. It's showing you using an Arduino with the kind of connections we do, resistor, an LED with a ground, and that's how you do a breadboard of, okay, simple connections, just simply two, one LED, one resistor. Okay, this is your output pin, and this is your ground. Okay, this is the pin which you're basically programming to make the output high or low. These are the IDEs of Arduino IDEs. We call it as sketch. This is a program going in. As you can see here, we're making the pin 13 high, making pin 13 low with a delay of 1 second, and that's when you do that, it's going to basically blink an IC, blink the LED. So some of the powerful microcontrollers have many packages inside them. Just showing you here, the all oscillators, ADCs, microprocessors, RAM, program memory. Very powerful. Like powerful means they have more integration, more packages inside one particular package. Again, there are some of the example of ARM microcontrollers. As you can see, so many blocks in there, integration. Again, powerful microcontrollers examples. And why we are talking so much about microcontrollers, because when we talk about automation, wherever it is, and let's talk about vehicles, there's so many microcontrollers being used inside smart cars. Okay, this is example 1. Again, the same thing, input, and the CPU will process that input to perform an output. And one of the most important element it is that there is a feedback which goes into an intelligent this goes as a feedback corrective action regarding what's going on, and that's autonomous vehicles or any other intelligent system you talk about. The feedback is one of the most important aspect of that particular system. And this is an example of a fluid level sensor. We're using an Arduino IDE with connections, and this is an LCD. And without going into the detail, this is just kind of circuit. If you want, we don't have time. Maybe in some other when we talk specifically about embedded systems or any other course, then we talk about the details. But simple is that these are the water levels, overhead tank, and this is a sample tank. It's basically monitoring the levels of the water levels, and when the water level will go below a certain, it's going to sound a buzz, and here's the buzzer, the output. And these are the commercial level, field level sensors. Okay, so some of the microcontrollers, their applications, and this is how I try to do when I'm offering a course relating to embedded system microcontrollers. Most of the courses, this is my kind of marks distribution: assignments, lab work, midterm, and the final exams. And these are some of the preliminary course requirements, kind of a high school, college, decent knowledge of logical reasoning, problem solving, mathematics and physics, basic understanding of programming. Again, kind of a clean diagram of another decent diagram of the main components of microcontrollers. I think we already talked about it, but this one has more, as you can see here, ADC, the comparator, PWMs, timers, brownout resets, watchdog timers, interval, visual reference, different other blocks inside the microcontroller. So popular off-the-shelf microcontroller examples: Raspberry Pi. This is from Expressive, ESP32, package of very popular ones. These are the Arduino's ones, and Texas Instruments, Infineon, Microchip, Silicon. Again, so many manufacturers relating to, or the microcontroller kits out there. But what I recommend, choose the one which are commonly used in the industry. Okay, so that will really help you basically kind of with your application, because why commonly used is because different experts have utilized it and they found it more adequate for their applications. So it means you can save a lot of time relating to what you try to do. Again, some tracking system for this is an Arduino project where basically a sun tracking system for solar cells. It will move the solar panels relating to the position of the sun. And this is the gas meter or water flow application, okay, using MSP 430 of Texas Instruments. So let's carry on. I think there are a lot of applications, but this is the Raspberry Pi. It's a gas sensor. I just want to, here, that's what I want to, come into. So we talked about microcontrollers. So now let's talk about FPGAs. So what is an FPGA? FPGA stands for Field Programmable Gate Array. It's primarily a digital, most of the time, a digital IC. But again, it has analog, some of the SoCs, system on chip, we call it as, it has the FPGA side, or the other side, which is the hard processor side, have ADCs or some analog signals. So we can call it as a mixed signal, SoCs, or mixed signals, FPGAs. Okay. So what is an FPGA? Why we use it? Basically, we can design most of the digital circuits using just simple programming. So like, for example, this is an inverter, and we are programming it using Verilog, one of the very popular language in programming FPGAs. The other one is VHDL. I'll shortly will show its syntax as well. So what we are doing here, we are making an input, and this is a 4-input kind of an inverter. So this inverter has, or this inverter module has 4 inputs, because it's 0, 1, 2, and 3. But if we just take this out, that if it's not there, then it's going to be a simple 1 input and 1 output. But in both cases, it's a 4 input and 4 output inverter module, and we simply write this line in order to invert A0 to Y0, A1 to Y1, A2 to Y2, and A3 to Y3. Okay, and if this syntax is not there, so it's basically simply going to convert or invert whatever is at the input A and assign it to. So see the ease, and so that is the reason of using FPGAs. It's very programmatically we can design digital circuits and systems. And this is the other language is the VHDL, and this VHDL is another very popular language, and this is the kind of syntax we use when we talk about VHDL. Again, the same thing. A 4-input inverter, and Y the respective outputs, and to do that we just simply write this syntax. Okay, we made this architecture. One entity can have multiple architectures, but in this case only one architecture, and most of the time only one architecture relating to one entity, and we just simply node it. So see, that's, so basically we are sorry, we can very easily program a digital logic design circuit system using FPGAs, and that is the reason of its popularity. But everything has its pros and cons. We are not going to discuss this here, but in simple words, this is what we are implementing. Okay, So 4 inputs and inverted outputs, and this is the, as we already know, this is the symbol of an inverter. So this another example, it's implementing not only so it's not implementing NOT, it's implementing other basic logic gates like AND, OR, exclusive OR, NAND, and NOR, using the Verilog language, defining an input A and B, which are, they are both 4 inputs, and the respective outputs are Y1, Y2, Y3, Y4, and Y5. And so Y1 is an AND outputs, Y2 are OR outputs, Y3 are exclusive OR, Y4 NAND, and Y5 are NOR, and that's how we are going to program it. In the equivalent VHDL side, that's how we do that, and this is basically the equivalent circuit inside the FPGA. So FPGA normally has only an IC which is only an FPGA only has this kind of an FPGA fabric. But now, because of a lot of integration, and so we have hard processors inside those packages as well, and we call those such ICs as SoCs, system on chip, because it has not only the FPGA fabric, but it also has the microprocessors. HPS means hard processor system, so it has microprocessors inside it as well, so that we can use one package for important industrial commercial applications. Okay. So this is an example of some of the most popular languages used worldwide. Currently, JavaScript is the top. Python is also very popular and famous. And the reason of showing you that it's good to know that which language to use for your applications. The most that's a different topic. But in simple, it's a good kind of a comparison chart. You should always keep in mind whenever you are trying to develop something. So what we are talking here relating to FPGAs, two of the most popular languages are VHDL and Verilog. Which one I should choose? It depends on your project, depends on where which geographical region you are living in and what are the norms there. So, and why I'm talking about because Verilog is pretty much like a C-like syntax, so that's why this arrow goes in here, and VHDL is more like a C++ kind of a syntax. Okay, this is just to show you that how you can remember VHDL and Verilog easily. So these are some of the leading FPGA manufacturers worldwide. AMD Xilinx, it's very popular. I have used both AMD Xilinx and Intel. I have also used Microchip Lattice, but the leading one is Xilinx nowadays because of the ease of using their tools. Altera, which is acquired by Intel, and Xilinx, which was acquired by AMD. Intel, they are working on improving their tools. Let's see how they goes. I haven't tried their latest upgrades, but anyhow, so the leading FPGA manufacturers worldwide are AMD Xilinx and Intel Altera. So these are the tools, Xilinx tools. It has Vitis, Vivido is a fundamental to program FPGA fabrics. Vitis for programming the hard processors. This is for the Python, and Vitis is again for AI/ML implementations solutions, and application prototyping and rapid developing. There is a PINC Python-driven platform. And Quartus are the tools. These are some of the tools relating to Intel's FPGAs. So now let's very briefly talk about what is a PLC. PLC stands for Programmable Logic Controllers. Because the hardware panels are very time consuming to wire, debug and change, GM identified the following requirements for computer control to replace hardware panels: solid states, solid state, not mechanical, easy to modify input and output devices, easily programmed and maintained by plant electricians, be able to function in an industrial environment. So what I'm showing you here is basically the fundamental blocks of a PLC. So it has a CPU, which is the brain of the PLC, like a microprocessor or microcontroller, whatever name you can give it. Here it's showing it's a CPU. It is a memory. It's an I/O kind of a unit. So these are the 4 fundamental units connected by address, data and control bus, and that's what we name it as a PLC. Okay. And a programmable logic controller is a specialized computer used to control machines and processes. It uses a programmable memory to store instructions and specific functions that include on-off control, timing, counting, sequencing, arithmetic, and data handling. And that's how they look, the PLC. Okay, this is the SCADA software used to program PLCs. Is showing from the Allen Bradley, very popular PLCs. And again, this is another picture showing the PLC in a rack to control. These are the Ethernet cables, some terminal blocks, I/O cards, breakers, and power disconnects. Okay, so again, PLC is used in industrial application. Just to basically give you a very brief overview why we use PLC and give you how it looks and how we interconnect. And these are the top PLC manufacturers: Allen Bradley, Siemens, Schneider Electric, Hitachi, Omron, and where they are located geographically. It's showing its location. So advantages of PLC control system: flexible, fast response time, less than simple wiring, solid state, no moving parts, modular design, easy to repair and expand, handle much more complicated systems, sophisticated instruction sets available, allows for diagnosis, easy to troubleshoot, less expensive. And let's have a demo, the PLC demo. Let's see. Okay, it's taking extra time. That's okay.
A programmable logic controller, or PLC, is simply a special computer that is programmed to control certain processes in industries like petroleum, steel, or automotive. Every PLC is composed of 3 main parts: input, CPU, and output. Suppose that we have an electrical motor and a push button. We want the motor to turn on when the button is pressed. When the button is pressed again, we want the motor to turn off. This function is similar to the function of the power button on your TV remote. To do this, we must first write a program for this operation on a computer and then download it to the CPU. Then we connect the switch to the input and the motor to the output. Now, if we press the button, an electrical signal will be sent to the PLC. The PLC input will deliver this signal to the CPU, but first must present it in a format that the CPU can process. Why? Because the CPU is a computer system and cannot process the raw electrical signal. The CPU will process the data received and send the result to the output. The output turns the data to a raw electrical signal again and applies that to the motor and turns it on. Now, if we press the button again, the process repeats and the motor will turn off. Okay, if you like this video, subscribe to stay updated with our new videos.
So this is what a PLC, a kind of a demo of a PLC. So let's keep going with our presentation. So that's kind of a brief overview of the PLCs. I'm just going to confirm that it's recording. Yes, it is. So let's carry on. So let's talk about what is an op-amp. It's basically it's an operational amplifier. Op-amp stands for, and why we use it. It has linear applications and it has non-linear applications. And in linear applications, we can use it as a adder or summing amplifier, subtractor or difference, voltage or current converter, current to voltage converter, instrumentation amplifier, analog computation, and power amplifier. In non-linear applications, means digital applications, we can build comparators, logic and anti-logarithmic amplifiers, multipliers, divider, integrator, differentiator, rectifier, peer detector, clipper, clamper, sample and hold circuit. So this is what the term stands for, op-amp, operational amplifier, and these some of the applications where we can use it. Temperature sensor, pulse sensor, gyroscope sensor, proximity sensor, magnetic sensor. And this is the symbol of an operational amplifier. Inverting input, non-inverting input, and it has an output. And that's basically a inside block diagram. What it does, it has a difference amplifier, the voltage amplifier, and the output amplifier. These are some of the IC packages of an op-amp. Okay, so just to show you, this is showing only one op-amp, but there are ICs which has multiple op-amps inside. These are some of the basic circuits of when we use an op-amp. This is an inverting amplifier, this is a summing amplifier, non-inverting amplifier, and this is the high-pass filter. Again, few more applications of op-amps. Let's talk about robotics. So what are some of the key parts of a robot? Okay, so this robot is primarily, we have already seen the demo in the beginning, and that's this what it's thinking is driven by AI, ML, and DL, and it's pretty powerful, strong. And this is the robotic arms used in car manufacturing, and this is the robotic arms used in airplane manufacturing. So what are some of the key parts of a robot? Number one, obviously, energy source, the motors, what we talk about, and we talk about sensors, switches, microcontrollers, DSPs, FPGAs, and associated intelligence electronics. And these are what this program, electrical electronic computer engineering, kind of electrical engineering and technology program is offered in their courses and projects, lab work to prepare you on. Okay, and so again, since we talk motors, so these are the different type of motors: AC, DC motors, special motors. Okay, and kind of a tree overview about the motors, and fundamental rules is the Fleming's left hand rule and the right hand rule when we talk about motors. These are the reference links. So, and I hope that with this demonstration presentation, it inspired the listeners about the programs relating to electrical, electronics, computer engineering, and technology, and will help them make a smart choice in their career objectives. Thank you very much. Take care.